Today, I'll be presenting a study called Analysis of the Leading Edge Erosion Impact on Design and Performance of Wind Farm Flow Control, a work that has been carried out inside the framework of the Horizon Europe IEA project led by CENER. If there's some people aware in the deep wind of this year, probably this presentation is familiar to you, but we have extended the analysis, so we have also new things for those ones. So let's get started with this. This is the, whoops, doesn't it go forward? Let me check. Yeah. So this is the index of the presentation we're following today. Okay. Typical index, introduction, methodology, case study, and then some conclusions. So we start with introduction. Leading edge erosion, well, as its name suggests, and you all probably know, is erosion that appears in the leading edge of a blade due to particles that are suspended in the wind, like dust or rain, for example. And it can have a relevant impact not only in the power production of a wind turbine, but also in its operation and maintenance cost. This type of erosion is especially relevant in offshore environments due to four main reasons. Okay? Because in general, the wind speeds are higher, because also the conditions are rainier, also because of the presence of sea salt aerosols, and because of reduced restrictions in noise. Leading edge erosion causes a loss in the aerodynamic efficiency of the wind turbine, which causes a power production reduction, especially at below rated wind speeds. But it does not only affect the power production, but also the thrust. Okay? And as it affects the thrust, also it modifies, actually reduces the wake a rotor produces. So it affects the interaction between the wind turbines in a wind farm, as you can see in this image that I'm sure you have seen thousands of times. So as it affects this, we believe that it could also have a relevant impact on wind farm flow control strategies. And in consequence, the main objective of this study that we carried out is to analyze the impact of leading edge erosion on wind farm flow control strategies. And today we'll be focused on the wake steering case, specifically in static wake steering case. So the general methodology that we carried out is represented here in this diagram. It consists of 6 main steps. Okay? The first one is to define the erosion categories. Okay? In IEA project, several erosion categories have been defined, but in this study, we have just used 3 of them. Erosion category 5, which represents low erosion, 7, which represents medium erosion, and 8, which represents high erosion. These erosion categories have the C form seen in the upper right image, but in the next slide, we will get more into detail these categories. So with these 3 erosion categories, we built 3 wind turbine models, aeroelastic models, using an OpenFast tool. And we have also built another wind turbine with no erosion that we, from now on, we will call clean. With these models, we obtain the thrust curves, the power curves, and this together with other parameters like rotor diameter, wind rose, hub height, and so on. We use them to build the wind farm models. And from this, we have used Flourish software. So we have a wind farm model for each erosion configuration, as you can see there. And we have also a 5th model, which is a mixed wind farm of erosion category 5 and 8. Okay, so in this case, we will give 2 wind turbines that are most of the time in unwaked conditions. We will give them high erosion, that means erosion category 8, And to wind turbines that are most of the time in wake, and they're awake, we give them a low erosion category, which is number 5. With all these wind farm models, we run flores optimizations to get the optimized geoangle set points, and with them, we calculate the annual energy production for the case without and with wind farm flow control. And last, we compare and analyze the obtained results. So as I said before, if we take a look at the erosion categories, we have them there in the table. We have that C form, and they are defined by 3 different parameters, HE, UE, and LE. And for this analysis, UE and LE have the same value. So for erosion category 5 and 7, HE is 0.12% the length of the chord, 8 is 0.20, UE and LE are 5% for erosion category 5 and 8% for erosion categories 7 and 8. And that gives us a maximum efficiency loss, aerodynamic efficiency loss, between 22 and 66% for the erosion categories chosen. It is worth mentioning here also that the erosion is only applied to the last 30% of the blade length, because it's the zone with the highest linear velocity, and along this zone, erosion is considered to be constant. So with these erosion definitions, we calculate the eroded polars using OpenFOAM CFD software. And with these polars, we build the OpenFast models I mentioned before. And we use them to obtain the power and thrust curves that we can see here. So as we can observe, the curves for the clean erosion category 5 and 7 are very, very similar. But the curves for erosion category 8 presents relevant differences. Okay, both in terms of power and thrust is much lower, especially at low and medium wind speeds. Okay. So it's important to notice here that it seems that performance of the wind turbine is highly sensitive to the HE parameter of the the blade profile. And as I said before, these 2 curves, together with other parameters, are used to build the wind farm models, and then this is used to calculate the optimized geoangle set points. So now move on to the case study. The case study that we've chosen is defined by the following parameters. Okay, the selected wind farm is the TotalControl reference wind power plant, which consists of 32 DTU 10 megawatts reference wind turbines, and it has the layout shown in the image. For the resource data, we have picked up the site resource data, which is the wind rows in the left, and for comparison purposes, we have also chosen another site, in this case Ulsan in Korea, because its wind rows is very different if you compare it with the site 1. And now for the mixed wind farm that I've mentioned before, as in the site, most of the wind comes from western direction, we have decided to give erosion category 8 to the wind turbines that are in the say purple rectangle there, and erosion category 5, I mean low erosion, to the wind turbines that are in the right part, means in the orange rectangle. The eroded blade profile is the one shown here, and as I said before, the wind turbines are modeled using OpenFast and wind farms in Flores. Now we're going to take a look at some optimized geoangle set points. In this slide, I show you a case of 7 meters per second wind speed, and we'll take a look at 3 different wind turbines that I've chosen, but the conclusion are the same one for the rest of wind speeds and the rest of wind turbines. So we start with wind turbine number 1, which is the one in that corner. And in the diagram, we can see U-angle set points with respect to wind direction. So as we can see, for most of the wind direction, especially when they from north to east, almost to south, U-angle set point is 0 because there are no wind turbines downstream, and therefore there's no need to yaw the wind turbine. And where there are wind turbines downstream, which is represented here by the gray shaded areas, the U-angle set point takes non-zero values. And as we can see here, the U-angles for the clean EC5, EC7, and EC8 configurations are very similar, but we see that there are some differences if we take a look at the mixed wind farm. In this case, for some of the wind directions, they take U-angles take higher values than for the rest of configuration. And this might happen because downstream there are less eroded wind turbines. Okay, so less eroded wind turbines can produce more power. So makes sense that the optimization algorithm gives more priority to these wind turbines that can produce more, and therefore this wind turbine, this case number 1, which is more eroded, is more yawed to maximize the overall power of the wind farm. So we move on to the next wind turbine. Now I've picked up number 20, which is in the middle of the wind farm. Obviously, the diagram is different because there are downstream wind turbines in a lot of wind direction. Conclusions are very similar to number 1. As I said before, when there are no wind turbines downstream, yaw is 0. Whereas I haven't said this before, but yaws are limited between 0 and 20 degrees in Flores. We have run simulations setting another limit, but conclusions are also the same ones. So as I was saying, yaws are 0 when there are no wind turbines downstream, and they take non-zero values where there are wind turbines downstream. And as in the case of wind turbine number 1, most of U-angle set points are very similar. And we can see here that in eastern and east-southern directions, the mixed wind farm takes smaller yaw values. And I think we are going to see it more clearly. Yeah, if we take a look at wind turbine number 32, which is in the upper right corner, this diagram for the clean EC5, EC7, and EC8 configuration is symmetrical to the wind turbine 1. But for the mixed wind farm, we see now more clearly that for some directions, yaw angles are slightly smaller, and that's because of the reason I explained before. I mean, now in the mixed wind farm, this wind turbine has less erosion, and there are downstream wind turbines which have more erosion. So the algorithm prioritizes power production with this wind turbine, even if we have more wake in downstream wind turbines, which have a higher erosion level. So now if we take a look at the AEP values, well, the first thing we can notice here is that obviously as erosion increases, the energy produced goes down for both the case without and with wind farm control. And we can also see that, as I said before, as erosion does not only affect the power but also thrust, we see that the AEP loss due to wakes, which is in the table on the bottom, is reduced when erosion increases. Okay, in this case from 7.5 to 6.8. It's not a lot, but we see this trend. And because of this, the AEP gain we get when applying wind farm flow control decreases too. Okay. Again, the values are do not vary a lot, but we see here that in clean we have 1.6% of AEP gain, and with EC8, which is the highest erosion we have chosen, we have almost 0.9%. That was with the side windrows. If we take a look at the case with the Ulsan side windrows, well, the values are generally, the AEP values are generally smaller because obviously the layout hasn't been optimized for these windrows, but the trend is similar. We see that the AEP weak loss goes down with erosion, and the AEP gain with wind fan flow control does the same. So you can see here that as erosion goes up, wakes are reduced, and therefore the AEP loss due to wakes is reduced too, and in consequence, the AEP gain we get when applying wind fan flow control gets smaller. And to finish with this, we jump into the conclusions. The first one is that the yaw set point for all the erosion configurations analyzed are very similar. Always, if the erosion is homogeneous inside the wind farm, if there are big differences, we have seen that there might be noticeable differences. The AEP of eroded wind farms is obviously lower than the AEP of the clean farm, and it goes down as erosion goes up, for both the case without and with wind farm flow control. The wake losses in all erosion configurations are kind of similar, but it's also true that it gets slightly smaller as erosion increases, and in consequence, the strategy optimization AEP improvement gets also slightly smaller, although as we have seen, their numbers are more or less similar. So all in all, we can conclude that for the analyzed case, erosion does not have a relevant or significant impact in static wake steering wind fan flow control strategies, as long as high erosion levels do not appear on some of the wind turbines in the wind farm. And these are the references that I've used to make this presentation. And that's all from my side. Thank you for listening. And now if you have any comment or question, I'll be glad to answer, or at least try it.